let's get started. So welcome everyone again to the field seminar for this week. So today we'll have Fred Galetto. He'll tell us about jets and clutters.
All right, thank you very much. So first of all, I should say I wrote down some notes that I'm happy to share for today's talk in case anyone wants them. And the work that I'm going to tell you about here is mostly coming from a paper with Mikaya Marino and Teresa Yu that we put on arXiv last summer. The story actually started as an undergraduate project with Elizabeth Helmick and Molly Walsh at Cleveland State. And then I should say Nick also helped me write a Macaulay 2 package for jets. So there's a little bit of different things that I might be referring to. So I want to start by giving you a very, very brief introduction to jets. And I'm going to start with an example. So I deliberately chose something very small because these things get big, but you'll see later why I also chose this one. So I want to start with just this ideal. The field here is really not going to be important throughout the talk. So I have this ideal, and it has a vanishing locus, which is some kind of variety, the union of two lines in the plane. And I want to tell you how you would construct the jets of this kind of space. So what you do is you take the generators, in this case, there's only one, and you do a variable substitution. Let me show you the first order jets. So for each variable, like x, I'm going to replace it by something like this, x plus x1t. And then similarly for y, y0 plus y1t. And then you expand and you collect powers of t. So we have a constant term. Then we have a degree 1 term in t. We also have higher order stuff here, but we don't look at it on doing the first order jets. I only substituted up to the first power of t. And then what we do is we extract these coefficients and we form a new ideal with those. So I'm going to do like a curly j here, j1 of I. And this ideal will be generated by x0, y0 and x0, y1 plus x1, y0. And it lives in this bigger polynomial ring with variables x0, x1, y0, y1. Okay. If you want to do second order, you would do something similar. Maybe I won't write the whole expansion out, but you now have to add another level, so x2t squared, and similarly for y. You expand, and you get the second order jets. You will have everything you had before, but now you'll have a coefficient of t squared that gives you a new generator. So that will be x0, y2 plus x1, y1 plus x2, y0. And this will be live in an even bigger polynomial ring. Okay. So let me maybe put down just a general recipe that will also show some of the notation that I use. So for me, I would prefer to avoid variables if I can. So try to do this in a not quite, but almost coordinate-free way. So I'm going to say x is a set of indeterminates, a set of variables, finite. And then for a natural number s, I'm going to define this other thing will be just another set of variables. It's the variables of the bigger ring that I saw over there. So I'm going to have that for every variable little x that I had in my original set, I'm going to have s plus 1 variables that I denote with subscripts. Okay. And then we define a ring homomorphism. We start from the polynomial ring with the original variables. We go to a polynomial ring with all of these new variables. But we also add the t, and we mod out by e to the s plus 1. So for every natural number, I'm going to have one of these homomorphisms. And what you do is if you, you send the variable x to xi t to the I. So if you now have an ideal I that belongs in your polynomial ring, let's say it's the defining ideal of some kind of variety, and you want to construct the jets of that, what you do is, well, let me make explicit the generators here. Let's say we have generators F1 through FR. Then what you do is you apply this homomorphism to every one of these generators, which does the kind of substitution that I showed you up there, and then you isolate the coefficients. So phi s applied to Fi will give you something that you can write in terms of powers of t. J goes from 0 to s. We mod it out at t to the s plus 1, so we don't care beyond that. And so we define this ideal of order s jets of I to be generated by these polynomials Fij. Okay? And then, of course, you take the vanishing locus of this in your bigger affine space corresponding to this polynomial ring over here, and you get the scheme of order S jets for the vanishing locus of I, if you want to look at the geometric side of it. I'm not really going to need it, but you could do jets for schemes of affine type over K that are not necessarily affine. So you just cover them with affine patches, do this procedure, glue everything back together. And I'm going to say the following, that I'm not a geometer. I'm not really an expert in jets on the geometric side. Excuse me. My understanding is that people in geometry use jets to do pretty fancy things in birational geometry, motivic integration, all that kind of stuff I wouldn't be able to tell you much about. But one thing that I think is true is that if you give someone a variety and say, please tell me what the jets of first, second, or third order look like, they wouldn't necessarily know in general, right, given the variety. So there's some progress, for example, on things like determinantal varieties of generic and symmetric matrices. There's a bunch of people that have worked on it. Kosir, Seturaman, Docampo, UN, Denegri, and Sbarra. There's a bunch of articles on this stuff. And then the other case that we understand is the case of monomial hypersurfaces, which is kind of a small case, but that one we understand. And that is due to work of Goward and Smith that I'm going to cite again in a moment, and also Cornelia UN. All right, so this is my general construction over here. And let me... Oh, sorry, yes, the dimensions we understand. Yeah, and other things we understand pretty well. Like if your base variety is smooth and irreducible, the jets are smooth and irreducible. Basically, you multiply by s plus 1, I think. Yeah, exactly. And maybe let me give you a sort of a sense of maybe a more basic intuition for these spaces. So let's even look at my basic example up there, x times y, right? So that's just the union of the coordinate axes in the plane. Now, suppose you have a point and that moves along these axes. Think about it in physical terms, right? Your point may be moving with a certain velocity vector, acceleration vector, and you can parameterize that. Say at time t equals 0, I want to have a position that's given by x0 and a velocity that's given by x1 and an acceleration that's given by x2, right? But how do I guarantee that my point with those parameters still moves along that variety? Well, it has to satisfy these equations for the new coordinates. So the velocity vector, acceleration vector, they have to satisfy these things. Yeah.
It's a geometry question, but can I think this space as I have a back point on a line, that it's a blank bed, I think that maps of that into my target space?
So you want to think of the space, let's call it Z, and this is like a fat point. Yeah. Oh, yeah, yes. Yeah. Absolutely. So I'll put it here. I wasn't planning to say that, but you can think that, so you can think that the points, so the K points on your order S jet ski, oops, sorry, thank you. They actually parameterize the, exactly as you were saying, order, well, these points into Z. Yep. And in fact, the jet scheme is the space that represents this functor, well, yeah, this functor right here.
People consider other fat points that don't live on a line or live on a plane.
Yes, I can tell you that actually Cornelia Wen looked at something called wedges, which is sort of the generalization where you put two variables like T and U. But I don't know exactly how far that story went. Okay, all right. So now I want to try and specialize a little bit to looking at the case of monomial ideals. That was also my example over there. And one thing you might notice immediately is that even if you start from a monomial ideal, the jets don't have to be monomial, right? Okay, but here's something you can do, which was actually proved by Goward and Smith. Smith is Karen Smith, and I think Goward was a student at some point. I couldn't tell you exactly, but and maybe 2006-ish, I want to say, mid 2000s. So if I is a square-free monomial ideal, then for every S, right, like we said, the jets are not going to be monomial, but if you take the radical of that, that would be a monomial ideal and necessarily square-free because it's radical. So is square-free monomial. And in fact, we can say a little bit more. We can say it's minimally generated I'm just going to phrase it this way, by the terms in the generators of the Jets ideal. So basically, if you've computed that, you just extract all the terms and you get your radical that way. So in fact, let me put the example down here. Again, if I start with I being just generated by xy, the first order jets, we know, we take the radical of that, it will have generators x0, y0, x0, y1, and then x1, y0. And then if you do the second order jets, you get all this stuff. And then all the new stuff. So that's x0, y2, x1, y1, x2, y0. In fact, when we coded this in Macaulay 2 with Nick, we said, well, radicals are kind of expensive computations, but if you've already done that kind of work to substitute there, just extract all the terms, and it's a lot faster that way. All right, so we thought about possibly try to combine the study of jets with some combinatorial ideals by looking at square-free monomial ideals. And so we gave the following definition. We gave it for graphs first with Molly and Elizabeth, and then later in this most recent paper, we extended to simple hypergraphs or clutters. I refer to the book of Rafael Villarreal, who calls them clutters, so I stick with that word. So we're going to say this. Let C be a clutter with vertex set x. So this is my set of variables. And then for a natural number s, the clutter of s jets or order s jets of C, which we denote as JS of C, is the clutter. Again, think simple hypergraph if you prefer, with vertex set given by all these new variables and edge ideal. This is, if I have my clutter, I would say I of that to denote the edge ideal. So the generators of this are the edges. Well, how do we define it? It's the radical of taking the jets of the edge ideal of C. Yes.
Sorry, I guess you said this already. The clutter is just a graph.
So if your graph would be a special case, right? So in a graph, we only have edges with 2 vertices. But if you do a hypergraph, you could have edges with 3 or 4 or different
So
sizes.
it's a hyper.
It's a hypergraph. But I guess they add the word simple because you don't want an edge contained inside another one. So yeah. But it doesn't hurt to just think about graphs for the purpose of this talk, really. So basically what you do is you do that, and then you have these square-free monomial ideals that they give you a bunch of new edges. That's how we define this new clutter. Okay, and to give you examples, maybe I'll put it here. I'll try to keep it around in case we need it. So again, now I'm gonna do an example with a graph, right? So G is path of length 1. Its edge ideal is exactly the one that I gave you before. And so what happens is that if this is your G with vertices X and Y, your J1 of G looks like this. You have X0, Y0, X1, Y1. And then you have those 3 generators that give you 3 edges, this, and that. And the J2 of this graph, now for every vertex you have 3, right? So X0, X1, X2, Y2, Y1, Y0. And now I have to put in 6 edges. The 3 that I had before, and then 3 more. Okay. And actually, maybe I won't write it down, but I'll tell you the pattern, which is not hard to see. You put in an edge in this jet graph. If there was an edge in the original graph, and if the indices on the variable, the subscripts, add up to 1 or less. So we're doing order 1, so we want 0 plus 0, or 1 plus 0, 0 plus 1. When you do order 2, now you can take anything as long as the subscripts add up to 2 or less. And if your graph is not a path graph, then you do exactly the same thing. It just becomes more complicated to draw. So, yeah. Okay. Yeah, of course.
The definition is only well defined because it's a theorem. Is that
Yes, it is. Yeah. So, to try and give you maybe a little more motivation for why we decided to do this, as I told you, in general, my understanding is that people don't necessarily know a lot about jets for specific types of varieties. And one thing that people don't understand in general is how these jet schemes decompose. If your base scheme is smooth and irreducible, so are the jets. But if your base scheme has singularities, then typically you will get components. And in general, it's hard to say how many you'll have, what their dimensions will be, what they will look like, so on and so forth. That is where we have partial progressing for determinantal varieties. And for monomial hypersurfaces, we know everything really, but that's a small case. So we thought about doing this because if you are interested in the components of these, so you're looking at the associated primes of these ideals, right? But one thing you can do is if you pass to the radical, which is what we're doing here, you retain the same minimal primes, which are sort of the effective geometric components, right? But what are the minimal primes of the edge ideals? They are related to things called vertex covers from combinatorics. So you can kind of marry this idea of studying geometric components by looking at the combinatorics. So that was our sort of philosophical motivation there. Okay. Yep.
So I'm guessing since you mentioned the hypersurfaces, if you don't have a version of this, if you leave out the first square free, that's the theorem that they get rid of. It's just a monomial ideal. Radical chip.
I think so. I think so. That paper of Goward and Smith, I think, does that too. Yes, but the part about the geometry of the monomial hypersurface is a later paper of Cornelia Yuen, and I believe she does the square free case. I could be wrong. Sorry?
Then why isn't what she's doing a special case of that?
It is a special case, right? But basically, if the if the original square free monomial ideal has more than one generator, then we don't understand the picture. Yeah, because she does a lot. Like she actually describes all the components. She describes the multiplicity of the jet scheme along those components. So in the case of one generator, she's able to do quite a bit. Okay. All right, so given these kind of pictures, then I want to tell you a little bit about some results that we get in our paper. One is motivated by what I was just telling you about, these vertex covers. And so let me talk a little bit about that. So I will still keep this notation throughout. So C is a clutter, X is the vertex set. So if you want to study vertex covers, one thing you can do is look at the so-called cover ideal, which in terms of algebra is the Alexander dual of the edge ideal. So what this means is that we form my new ideal. Now the generators of this one are the minimal vertex covers of C. So you kind of swap the role of minimal primes and generators. But let me also give you an alternative version of thinking about that, and also its symbolic powers, which is what I care about next. So without giving you a general definition or reminding you how these work, I'll tell you what they look like for cover ideals of clutters. So whenever you have an edge, let's say x1 through xr, so this E of C is the set of edges of your clutter. Whenever you have an edge, you form the ideal generated by the vertices that make up that edge, and you take its kth power, you intersect them all up, and this gives you the order k symbolic power of the cover ideal. So if k is 0, then you just intersect all the edges, and that's how you get this cover ideal. And I will also add that the generators of these have some combinatorial interpretation. So a K cover of C is a monomial in this order K symbolic power. I should have added space for the word minimal here and minimal generator here. But let me just show you with a small example what happens. So again, I do my favorite thing here. Just a small example. Not the most interesting because we won't have to intersect, but just to give you an idea. So the path of length 1 has 2 minimal vertex covers. So let me go back to this picture for a second. What is the idea? If you haven't seen this before, so the idea, you maybe think of this graph as, like a network of secret tunnels, and these points are the intersections, right? And you want to place guards at the intersection points so that they can monitor all the tunnels at once. And if you want to do it minimally, you want the least number of guards, right? So you can put a guard here at X, and they will see the only one corridor we have in this picture, or you can put a guard at Y. And so that's why here I have my generators that are just X and Y. Okay, but if you take now this third symbolic power, again, not the most interesting case here because there's no intersection, but that means we can do it very quickly. We only have this one edge. We take the third ordinary power and we get 4 monomials. And these monomials correspond to k-covers. What does this mean again? Suppose again you have your network of tunnels, and now you want 3 sets of eyes on every corridor. Okay, then you can post 3 guards over here and 0 over here. Or you could put 2 guards over here and 1 over here for this second monomial, and so on. Okay, of course you could have more, but if you do it for the minimal generator, these are the minimal 3 covers and 2 more. Okay, so that's my very quick background here for combinatorial commutative algebra. And I want to use this to tell you about one of our main results here. I just need to tell you one more thing. So we have our various rings with the various variables. I guess you could see it here. This is what I'm referring to. So you can define a map. I denoted delta S. It goes from the ring with all the variables with the subscripts back to the original ring without the subscripts, and it sends a variable xi to just x, forget the subscript. And in a sense, the opposite of this map will be familiar to people that work with monomial ideals. If you have a variable x, you can replace it by a bunch of variables, x0, x1, x2, x3, and that's what you call polarization. So I call this map depolarization. It's not like I want to be different and I don't want to use polarization, but this is the advantage of being a ring homomorphism. So we like that a little bit better for our purposes. And we use this to state one of our main results here. And let me write it and then we'll unpack the notation. Because sorry, but there's all the notation coming together in one place. Okay, 1, 2, 3, 1, 2, 3. Yes, okay, so let me walk you through what I mean by this. You start with a clutter. Think our graph, our path of length 1. You form the clutter of jets of some order. So these pictures again that we've been doing, right? So you have one of these. Now for one of these, you consider the cover ideal, regular covers. You depolarize. What you get is a certain symbolic power of the cover ideal of the original clutter. Okay, so basically this tells you can go back and forth between the two. So if you want to understand the minimal vertex covers of jets, you could just study the symbolic powers of these cover ideals. And let me tell you, this is nice, but it's also a bit of a bummer because it's known that these are pretty hard. So it tells you that study minimal vertex covers of jet graphs or jet clutters is as hard as understanding symbolic powers of square-free monomial ideals. All right. I will just give you a little corollary of this that hopefully will make it a little more tangible. As a result of this map, if you restrict it to minimal generators, it will give you a bijection. So let me say the minimal vertex covers of the clutter of jets of order S are in bijection with the minimal S+1 covers of the original clutter. So this is sort of the combinatorial version of that statement above. Yes.
I know you wanted to do depolarization, but why wouldn't you want to phrase it as the polarization of the?
Yeah, as far as this statement is concerned, either one is fine. I think for the proof, we found it a little more convenient because we actually wanted to show the ideals were the same.
Okay.
So it was a little more convenient to have a ring homomorphism. All right.
Oh, trying to introduce depolarization, right? So the question is like, why not do it the other way around? Take it the power of the ideal and polarize.
Go backwards.
Go backward.
Yeah, so for this statement, either one's fine, right? We also have a very specific notation, right? We want to start with x0, x1, you know, polarization, maybe different people write it different ways. So maybe that. So then to show you maybe something more concrete, what if we're actually going to do it with polarization, right? We have this example over here. So we can use that information to say, again, if your graph is just a path graph, so the one pictured over there, then the minimal vertex covers are, there's 4 of them, you polarize those monomials, so you get x0, x1, x2 as one of them, x0, x1, y0, x0, and then y0, y1, and finally y0, y1, y2. And this was not very strategic to have the example over here and the picture over there, but just to show you one of those covers on this picture, let's say we do the second one here, then that would be highlighting this vertex, and that vertex over there. And notice that you always have to do it starting from the bottom, right? It's like, what's the game called where you have to drop in the chips and form like lines of 4? Connect 4? Thank you. So you just drop and it always falls at the bottom. Before you put a chip over here, you have to put one over here if you draw graphs this way. Okay, so questions, comments? Yeah. Yeah. What about that bundle? Uh-huh. Yeah. Okay. I don't see it that way. I suppose you could if your clutter has a single edge, then the edge ideal is the ideal of a monomial hypersurface. So I guess in the right setting that will give you a curve, and you could think of it that way. All right, so very briefly, I'm gonna say our motivation for writing that theorem on top of understanding, as I told you, the connection between covers and components was also something else. So when we did the undergraduate project, we were looking at properties that jets might preserve when you apply them to graphs. We first look at the property of being well covered. So that means all the minimal vertex covers have the same cardinality, and the jets do not preserve that. Fails pretty quickly. Take the complete graph. So then we looked at a smaller class of graphs called very well covered. I know. And in that case, all the minimal vertex covers have the same cardinality, and that cardinality is half the number of total vertices of the graph. So it's very specific. It's a small class. But we looked at a lot of examples, and it seemed like that was preserved. So then we made it a point to try and prove that statement. And we were actually able to prove that statement by combining that, where's the theorem? This theorem over here, together with some results about symbolic powers. In fact, the symbolic Riesz algebra of the cover ideal of a graph has a very nice explicit description. You need to only take generators of degree 0, 1, and 2, so corresponding to 1 covers and 2 covers. Those are described. You just need to check those of the right dimension, the right cardinality, and then the statement falls out of that. I should also say, however, that unbeknownst to us, someone had essentially proven that result already. This person, his last name is Sayed Fakhari. But they were doing something completely different. They weren't looking at jets. They were interested in ideals that have linear free resolutions whose symbolic powers also have linear free resolutions. And that class of ideals is actually the class of edge ideals of very well covered graphs. And that person did the proof by essentially constructing the jets of those graphs without applying the jets idea from geometry. But I think it's interesting to have that kind of connection. It would be interesting to generalize this statement about very well covered to clutters, uniform clutters, but I have no idea how to do that. We thought about it, but all right. So then I have maybe 15, 12 minutes or so. I'll try to give you, I wanted to tell you about another result that does something slightly different. So I guess I have to go back to my drawing board for jets here. So maybe I won't give you a formal definition of this part, but I'll try to draw a picture. So suppose you have your scheme or variety, whatever you like, and let's say it has singularities. When you look at the jet scheme, it has a bunch of components. So you may have a bunch of different stuff over here. That's a lot. Just various components. So there's a natural way to project from your jet scheme to the original variety. If you think about the variables the way I labeled them, this is all the variables x0, x1 to xs. You forget x1 through xs, and x0 goes back down to x. So there's a nice projection. So let's say you have singularities. So you have a singular locus. You can look at the preimage of the singular locus in your jet scheme, basically leave that out, and you get some open set, but then you look at the Zariski closure, and you get something interesting. You get something that is, in some sense, a big part of the jet scheme. It has full dimension, the same as dimension as the jet scheme. And this is referred to in the literature as a principal component. I'm going to write PS of Z. The name is a little bit misleading because if you start from something that is not irreducible, this principal component is not a component, is not irreducible. So this is the picture version of the definition that's given in those papers. If you wanted to do something algebraic, you would have to say if this Z is the vanishing locus of some ideal, then you could do something like this. You take your jet scheme, you remove the pre-image of the singular locus, you get something that you close up, and then you take the vanishing ideal of that. I'll spare you the details. You can write this in a slightly nicer algebraic way because taking differences corresponds to taking colon ideals and so on and so forth. But I'd rather just tell you what happens if you do this for square-free monomial ideals, which is the part we care about. And so I'll just tell you here that story.
So you said, yes, you said like principal component, it need not be irreducible.
If Z is irreducible, PSZ is irreducible.
Is it supported only on the component corresponding to Z, like the,
But if we're assuming this is irreducible, there's only one component on here, right? So yeah, if you restrict that projection to the principal component, you get a dominant map onto here. So it essentially covers
yeah,
everything.
I guess I'm wondering, like, can you get other components of the jet, like somehow?
No. No. So in a sense, this PSZ is kind of like the nice part of the jet scheme. And maybe to try and give you a sense of why it's nice for monomial ideals, let me write down what happens in that case. So let me do the same setting. You have a C, a clutter, a vertex set X, you take its edge ideal. Let me also say we want to write minimal vertex covers of that C. So then I'll give you two descriptions of this. We call it ideal of principal jets. We don't want to call it principal components, so ideal of principal jets. You can actually describe it by giving a primary decomposition. For each one of these components, Wi, you just take the jets of that. So remember, this Wi is just a set of variables, x, y, z. So applying this JS to a set of variables means now I'll have x0, x1 to xs, y0, y1 to ys. So just more variables. Intersect, you get this. Or the description with the generators is you'll have a generator x1, I1, x, r, IR, whenever you had an edge of your original clutter and the other indices, the one that index the jet variables, can be anything you want. Yeah.
So Wi is a minimal vertex cover.
Yep.
So do I take the induced subgraph on that?
No, you just consider that as a set of variables. Yeah. Yeah, sorry, I use this JS thing and apply to different things. So if you apply to an ideal, you get an ideal. If you apply to a set of variables, you get a set of variables. If you apply to a clutter, you get a clutter. And maybe I should put the picture over here so you can see what happens. This is again a square-free monomial ideal. So there's some kind of clutter attached to it. And you can guess we call it the clutter of principal-less jets. And again, let me do my simple example. If this is a graph G, and what does P1 of G look like? Again, I have to have on my variables x0, x1, y0, y1. But now you put in all the cross edges whenever you had an edge in the original graph. So maybe again, not very strategic, but if you want to compare, the clutter of jets has that many edges, the clutter of principal jets has more. But in a sense, it's more and it's in a nicer way. It's more regular. You have all the possible ones going across. So in this sense, it's a little bit nicer. So if you do P2, you get this. Okay.
So I think that's like a graph expansion.
So people have told me about this. Again, I'm not also a combinatorialist, but people have pointed to some constructions here. And I looked at the literature. They talk about disjunction or disjunctive product of this graph and then the empty graph with 3 dots corresponding to these. Yeah. We don't know of a nice combinatorial construction for these, but the fact that these are nice, again, lines up. Okay. So, yes. Yeah, of course. I should say, I mean, these are actually, none of these results require particularly deep proofs. This requires, a little bit of algebraic work. There's some lemmas, but the ideas are not super difficult or not too fancy. So I wanted to conclude, I have probably like 3 minutes left, and I wanted to tell you a little bit about the fact that we study invariants like the Hilbert series and the Betti numbers of the edge ideals of these. Really, to do those, we kind of phrase it in a slightly different way because it's a little more convenient. We just say, suppose you take a square-free monomial ideal and you do this principal jets construction. So basically what we do over here, then we're able to find out things like the Hilbert series and the Betti numbers of the principal jets, which is again something we cannot do for the regular jets. So I do need to tell you one thing for that statement, so bear with me just a couple more minutes. All right, let me narrow it down to what we need exactly. Okay, so we need this thing. We call this a lifting function. So we denote it L sub s. It takes as input 2 natural numbers. It returns a natural number. 0 is allowed. So it counts the number LSJK of ways a set U in X with cardinality J lifts to a set V inside JSX with cardinality K along the depolarization map. This is a very weird thing. So let me show you the example because it will be hopefully much easier to understand. So let's do the easiest case here. So suppose we have a point on here, X, and you have order 1 here, so X0 and X1. So L1 of, what am I doing here? 1, 1 means that I have this, the map goes down here, right? So I have one single point over here. I want to count in how many ways I can lift it to 1 point over here. So 2 ways. Right? But what if I have a point down there and I want to lift it to a subset of cardinality 2? Then I have to take both. So there's only 1 way. Notice that this would still be true even if I had more variables here that are not participating in this process, right? So it doesn't really depend on the set X itself. But to give you maybe another example, if you do 2, 1. So if I have my 2 points on here, can I lift it to a subset of cardinality 1? No. But if I want to lift it to a subset of cardinality 2, then I can choose these 2 points, or I can choose these 2 points, or I can mix these two, or mix these two. So I have exactly 4 ways to do that. And so we need this because we actually take these values and we put them in a matrix. And if you do that, something kind of funny happens, which we thought was really cute. And again, not strategic on my part at all here, but this is ready to go. So here's my example. You have your simplicial complex. So 1, 2, 3, 4, 5 vertices, a 4 triangle. Wait, yeah, 4 triangles filled in. So those are 4 facets of dimension 2. It has a certain F vector. So face of dimension -1, 5 faces of dimension 0, 8 faces of dimension 1, 4 faces of dimension 2. And if you know the F vector, you can actually compute the Hilbert series of the Stanley-Reisner ideal of this thing. Okay, so the goal was the Hilbert series, but we just do it with the F vector. Well, what happens is that you form your, I do order 1 principal jets. You get some other square-free monomial ideal, so it corresponds to a simplicial complex that I call gamma 1. The F vector of that is obtained by multiplying the F vector of delta with this lifting matrix that I told you about a moment ago of the appropriate size. So the entries here are values of the lifting function. This would be L1, 0, 0. This would probably be L1, 1, 1. I guess this is the one we computed, L1, 2, 2, right? So you multiply, you get the F vector. And here, if you look at the Benny numbers, which again can be obtained combinatorially using Oxford's formula from the simplicial complex over here, you have to do one thing that's a little bit funny. You have to take the first row and push it to the right 1 unit. You have to take the second row, you have to push it to the right 2 units. And you get a matrix that looks like this. But then if you have this matrix and you multiply it with this lifting matrix of the appropriate size, then you get a matrix. And if you push the rows back in the right place, then you get the Betty table of the first order principal jets for the Stanley-Reisner ideal of delta. And we thought this was kind of cute. I don't really know of any other families of ideals where you can just get sort of higher order information by doing something linear like this. And also, again, one motivation for it is that in the case of determinantal varieties, specifically the 2x2 minors, if you look at the first order principal component, Gorpade, Jonoff, and Sethuraman computed the Hilbert series of that the jets of that determinantal variety, sorry, the principal jets. And they found that the Hilbert series of that is the square of the Hilbert series, the original variety. So there's a very nice connection. We thought, what happens for monomial ideals? Well, it's not the square, but it's some kind of linear relation on the F vector and on the Betty numbers. So sorry for going over time.
Thank you, Brett.